So now let's talk about the basis of vector space. So what is the basis of the vector space? The basis of the vector space is that vector space which is linearly independent and which spans the entire space. So if a matrix or if the number of vectors are linearly independent and if it spans the entire space, so that forms the basis of the matrix or the vector space. So see, the two vectors cannot span. So for example, if we have the three dimensions, that is R power 3 dimension space, and if you have only two vectors, then it cannot span. It means it cannot fill that three-dimension space. So that is what it means. Though they are independent, it doesn't matter. So like the four vectors cannot span. Now if I have four independent vectors, four independent column vectors, and we have R power 3, then also it uh, cannot span the entire space. So we want enough independent vectors to span the space, so that is, we call it as the basis. Now let us write the definition of this basis here. So the definition goes like this: a basis for a vector space is a sequence of vectors with two properties. So what is the two properties? That is, the basis vectors are linearly independent. So that we already seen what is the meaning of linearly independent. And the second property is that they span the space. So the two condition for the basis is that there has to be the vector has to be linearly independent and they span the space. So that is what it means. So let's take a few general examples here. So there is a one and only one way to write the v as a combination of basis vector. So if we take the vector v, then we will see that whether this is a basis or not. So that, for example, v is equal to, we have a vector that is va1 into v1 plus it is added with multiplied with all the scalar values, and then a2 into v2 plus dash dash plus an into vn, and also we have a vector v, that is another vector v, that is b1 into v1 plus b2 into v2 plus etc plus bn into vn. And by, if you subtract this both the vectors here, so then I have a1 minus b1 into v1 plus etc, like this we have, plus then we have an minus bn of vn is 0 if this is equal to result in the 0 vector. So from the independence of v, each ai into bi is equal to 0. So then ai is equal to bi. So ai minus bi is equal to 0. Then we have ai equals bi. Then there are not two ways to produce v. Okay. So don't worry, we'll talk about the examples and you will understand what is the basis vector means. So now let's take a simple and standard basis function here. So we will talk about the solving this basis vector and finding the basis vector in this tutorial. So let us take an identity matrix here with 2 cross 2 identity matrix. So if you look into this 2 cross 2 identity matrix, then what is the space of this dimension, or the dimension of this matrix is R power 2, because there are 2 rows. Then since we are talking about the column vector or the column space, then it depends on the number of rows. So R square here, and we have the 2 pivots. So this forms the independent and basis. So this forms the basis vector. As per the definition, what are the 2 properties? So the 2 properties is that the basis vector are linearly independent and they span the space. So whether they are independent, yes, they are independent, because if we see these vectors here, that is 1 and 0, these are independent because uh, uh, these are independent um, because if you see here, there are two pivots here, and there are two, and the rank of and the dimension of the matrix is also 2, and the rank of the matrix is also 2 when R is equal to n. So it's linearly independent. So now let us call this vector I 1 0 as I and 0 1 as j. So they are independent and they span in R square. So likewise, um, the vector here is span for a three-dimension case. We need such. So here we have two vectors, it is I and j. For three-dimension, we need three vectors similar to that. So that is I, j, and k. So now we'll talk about the example, and the particular example for this basis function here. So let me save this page. Okay, so let's take the vectors. Suppose we have vectors here, say as we discussed for a three-dimension case. So the dimension is a three-dimension case here. It is R power 3, where we have this minus 2, and we have the second vector as column vector as minus 2, 1 and 4, and the third one is 0 3 1. So now there are how many vectors? There are three vectors. So if we generalize this, so this is I, j, and k vectors. Now if I, j, k vectors, if you put them into matrix form, so then it is let's take this minus 2 0 0 1 3, sorry, it is 1 4 1. Alright, so now let us call this as a matrix A here. So now we solve this, we'll reduce this matrix by same echelon reduced form. So now what we'll do is that we'll subtract this uh, row 3 minus row 1 here. So I'll just write this E3 minus E1. So the first row remains to be as it is. So this will be 0 minus 2 0, and the second row will be 0 1 3, and now so this will become 0, and this will become, subtract this will become 6, and this becomes 1. So remains to be as it is. So now we are in the middle. So now I have to take out this 6. So to take out this 6, then what I will do is that then I will subtract this E3, the new E3, with minus 6 times the new second row, that not new second row, with the second row. So then what do we get is that 1 minus 2 0, and then we have 0 1 3, and then this is 0. So if you multiply this with 6 and then subtract, I'll get here 0. If you multiply with this 6, so what do I get here? Did we miss something? Okay. 18, so 18 minus 1 I'll get here as here we got something else. So here we have minus 17 we get. Something is missing. We got these 4s, then we have 4 minus 4, it's 6, and this gets 4. So we have this minus 17. Okay, so let's see what we get here. So I will copy this and I will paste here. So now we will continue this elimination process. We'll take out these threes here, so above. So what I'll do is that, so now uh, I'll multiply this third row, so then now it is like E2 minus 17 by 3. Not 17 by 3. So I need to get it here. Sorry, not 17 by 3. So I have to take this as 3 by 17 into E3. So then I'll get this form as 1 minus 2 0, then I'll get 0 1, here I'll get 0, and this is 0 0 minus 17. So then what I do is that I'll take out this minus 2 here. So to get that minus 2, then what I'll do is this E1 minus it is basically we need to add it, so I multiply with minus 3 and then I'll add it here. So we'll add this by multiplying with minus 2 into E2 here. So then I'll get the first matrix as 1 0 0, and this 0 1 0, and this is 0 0 minus 17. So now to bring it in the reduced and identity form, so I'll divide the pivots by itself. So then finally I'll get this in the form as 1 0 0, and this is 0 1 0, and this is 0 0 minus 1. Or we can divide by minus 17 itself, so that I can get here by plus 1. So now if you see here, the rank of the matrix R is equal to 3, and the columns the n is also equal to 3. So now this is perfectly, it is independent, means all three columns are independent and they can be combined to form the basis, or they can combine to fill the three-dimensional space. That is the three-dimensional space. Here the space is R is equal to 3. So now this forms the basis. Is this a basis vector? Yes, this is a perfectly, the matrix A is a basis vector. It is independent and it will and it spans the entire three-dimensional space. So now let's take one more example here to understand whether that matrix or that vectors are the basis vector or not. So let me save this page here. So this is page 9. Take the new page. So now let us take the new vectors here. So the new vectors, the same thing, we will change the third column. So we'll take 1 0 1, then the second vector is minus 2 1 4, and the next vector we take this as minus 1 1, and this is 5. So now we have changed just changed the third vector here, and let us put this all three vectors in a matrix form here. So then we have 1 0 1, then minus 2 4, sorry, minus 2 1 4, and this is minus 1 1 5. So now let us bring this to a reduced echelon form. We'll follow the same process here. So what do we do is that is E3 minus E1. So then the first row remains as it is, that is 1 minus 2 minus 1, and second row also remains as it is, 0 1 and 1, and the third row, so this will become 0 here, so this will become 6, and this will become also, this will also become 6. So now we have to take out this 6 here, but if you see the both are 6, so if you try to take out this 6, then we get the third row as completely 0. So we'll get a 0 vector here. So E3 minus 6 times the E2, then we get the vector here in the form as 1 minus 2 minus 1 and 0 1 1, and this we get this as 0 0 0. So if you see the third row, we will get here as the 0. The third row is 0, it means rank of the matrix here. We can go further, we can eliminate this minus 2, but there is no point of discussing. We can eliminate this minus. Okay, fine, we will do that one also, and then we will talk about the final whether this is basis matrix or not. So now let us remove even this minus 2 to bring it in a reduced form, so that we will get it by um, E1 plus minus 2 of E2. So then we will get the final matrix, the reduced matrix, as 1 0. So if you multiply with this as minus 2 and then we'll perform this, we will get this here as minus 3 here. So we'll get 0 1, and here I'll get 1 and 0 0 0. So now this is in a perfectly in a reduced matrix form, that is R is equal to this. So now if you see, we have only the two pivots, that is in the first column and the second column, therefore the rank of the matrix is equal to 2 here, and the number of n is equal to 3 columns, therefore it is not linearly independent matrix, it is a dependent matrix in this case, and it doesn't fill the 3-dimension space, therefore this is not a basis vector. So this is the how we can find whether the vector or the matrix is a basis vector or not. So if we generalize these terms here, then we say, let me write the generalized term in terms of statement here. So if you have the vectors v1 up to dash 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 up to vn, or basis for say r power n, exactly when they are the columns of an n by n invertible matrix. Thus R power n has infinitely many different bases. So let me fill the spaces here, so it forms the R power n and here the R power n. So the vector v1 to vn are the basis vectors for R power n exactly when there are the columns of an n by n invertible matrix. Means if we have exactly n by n invertible matrix, so thus the R power n has infinitely many different bases. It means we can generate as many as bases. And the second definition is that the pivot columns of A are a basis for its column space. So this is another point here. So let me write that point here. The pivot columns of A are a basis for its column space. So the pivot columns of A are the basis for its column space, and pivot rows of A are the basis for the row space. So if we take one more example here, we'll just take a quick example and see whether this is a basis or not. Um, a 2 cross 2. So let me save this page here. So if I take one more matrix here, so if I take a matrix A, which is of a 2 cross 2 matrix here, that is 2 4 3 6. Let me write it neatly. That is 2 4 2 4 3 6. Now if you bring this to the reduced form, so the reduced form, so only thing is that if you see here 3 and 3, if I multiply this with 3, so I need to, so then it will come into 1 into 2 and 0, it's 0. So here we have the rank of the matrix R is equal to 1 and the number of columns is equal to 2. Again, this is not an independent matrix, though we can say that the rank of the matrix is 1. So only this column might be independent, but this will not fill the R square, means it will not fill the two-dimensional plane. We have one independent vector, but the other vector is not independent, therefore we don't call it as a basis vector or a basis matrix this. So that is all about the basis matrix. So thank you. In the next tutorial we will continue with the dimension of the vector space.